Hello students, this is Mahesh Javalkar from Maratha Polytechnic, and today I am posting my next video on analog electronic circuits in which I'll be explaining about RC coupled amplifier and its frequency response. So here the heading will be RC coupled amplifier and its frequency response. Okay, so we will see the contents of this. First we will see what do you mean by small signal amplifier, circuit diagram of RC coupled amplifier, frequency response of RC coupled amplifier, advantages of RC coupled amplifier, disadvantages of RC coupled amplifier, and applications of RC coupled amplifier. So next, first we will see what is small signal amplifier. Okay. Now small signal amplifier by definition is generally referred as voltage amplifier because they usually convert a small input voltage into a much larger output voltage. So as I've shown in this block over here, a small input voltage here at the input is converted into a large output voltage. Okay, so here you can see a small input voltage. So this is your small input voltage. So this is V in input voltage, which is small in magnitude. Okay, so that is converted into a large output voltage. This is V out, and this you can see there is a phase reversal of 180 degree, and it has been amplified, and this is a large output voltage. So this is your performance of a small signal amplifier, which is amplifying the voltage of the input signal. So voltage of the input signal amplified. So at the input you have small input voltage, and output you have large output voltage. Okay. Then we'll go to see the circuit diagram of RC coupled amplifier. Now here you can see the main component which will amplify is your transistor. So here is your transistor. Okay. Now this transistor has three terminals. This is base, this is collector, and this is emitter. Okay. So it is connected in common emitter configuration. So here you can see this emitter is common to the input circuit, and this emitter is common to the output circuit also. Okay, so it is a common emitter configuration. Okay, then we will go to this VCC supply, what is given here. So this VCC supply is nothing but a DC voltage. DC voltage. Okay. Now this DC voltage is given and it will make a current to flow. So current will flow in this path. That current which flows in this path will develop a voltage across R1. So here a voltage will be developed. This we can call it as VR1. And here also a voltage will be developed. This we can call it as VR2. Okay. Now VR1 and VR2 are the biasing voltage. Now this voltage will see that the transistor is properly biased. Properly biased means because we want to use it as an amplifier, the base emitter junction, the first junction of the transistor should be forward biased. So here it should be forward bias. Okay, and here it should be reverse bias. Okay, and the base collector junction should be reverse bias. Okay, so that has to be maintained with your DC voltage, VCC, whatever you give. Therefore, here R1 and R2 are called as biasing network. So this is voltage dividing biasing network. So R1 and R2 is used for biasing the transistor. Biasing means you're applying a DC voltage, a proper DC voltage to the transistor so that it operates in active region. Active region means base emitter junction is forward bias and base collector junction is reverse bias. Okay, we want to use it in active region because we want to use it as an amplifier. Okay, then there is a resistance Re over here. So Re is in the emitter line. So here you can see Re is there. Now this Re will develop a certain voltage across it. That voltage no doubt will decrease the gain of the amplifier, but it will see that the operation of the amplifier is stabilized. Stability is maintained. Okay. If the voltage across Re becomes more, then this parallel capacitor across Re, which is called as C, will take all the AC input and give it to the ground so that less voltage is developed across RE and stabilization is also obtained. Okay. And then here you see a resistance RC. Now this resistance is your collector resistance, which is large in magnitude. You have base collector junction, which is reverse bias here, and this resistance value will be large. So current flowing as collector current here will develop a large voltage across RC, and that will be taken as your V out. Okay. Then you have a capacitor C in here, C in capacitor. So this is called as a blocking capacitor. This is called as blocking capacitor. And now this will block block DC, and it will pass AC, so that AC reaches the base of the transistor. Okay, so this is your signal, whatever you are going to give here. So this will be your V in. Okay, and this is what the alternating quantity has to reach to the base of the transistor. Okay, so here you can take the output after the C out. So here you can see this will be your output here, which will be a large voltage. Okay, okay, large voltage output. Now here the basic amplification takes place because of the transistor only. The transistor, the base emitter junction here is forward bias and base collector junction is reverse bias. Okay, so the resistance of the base emitter junction will be less and the resistance of the base collector junction will be more. So you are transferring from low resistance to high resistance. So it is transfer of resistance. Okay. Now whatever input voltage develops a base current here, that base current at the output, that is collector current here, will be in large magnitude. It will amplify because the transfer of resistance action of the transistor, and transistor will amplify the output current. This current flowing through this resistance RC will develop a large voltage at the output. Hence, we say there is a amplified voltage at the output. So this is how your RC coupled amplifier is going to work. Okay. So these were the component description and working of the amplifier. Okay. So next we'll go to see the circuit explanation. Now same thing as I've told you in this circuit explanation. First one is a capacitor C in at the input acts as a filter which is used to block the DC voltage and allow only AC voltage to the transistor. If any external DC voltage reaches the base of the transistor, it will alter the biasing conditions and affects the performance of the amplifier. This is very true. Then second point is R1 and R2 resistors are used for providing proper biasing to the bipolar transistor. R1 and R2 form biasing network that provides necessary base voltage to drive the transistor in active region. Now we want to make the transistor work in active region only because we are going to use it as an amplifier. Okay. Then third, RE resistor is used for stabilization. Then fourth, a capacitor CE, emitter capacitor CE and emitter resistor RE makes negative feedback for making the circuit operation more stable. So stabilization is achieved. Then fifth point, the coupling capacitor C out transmits AC signal but blocks DC. This prevents DC interference between various stages, the next stages of the amplifier and the shifting of operating point. Okay. So that will not interfere with the next stage. So it will block DC and pass AC to the next stage. Then as a whole, I've told you the circuit operation mainly depends on the transistor. The transistor, because of its own feature, is used in amplification when you go from lower resistance to higher resistance, transfer of resistance. So input current, base current will be very small in magnitude and the output current, that is collector current, will be large in magnitude. Okay. So this operation in short, you can tell that when an AC input signal is applied to the to the base of transistor Q1, it gets amplified and appears at the collector load RL, which is then passed through the coupling capacitor C out to the next stage. Okay. Then we'll go to see what do you mean by frequency response. Okay. Now, whenever we say frequency response of a certain circuit, we always state that frequency response is a curve, that is a graph that indicates the relationship between voltage gain and function of frequency. So you have to draw a graph that will indicate the relationship between voltage gain and function of frequency. So here you can see, if you draw something like this, y-axis and x-axis. So x-axis will be frequency in hertz, okay, and y-axis will be voltage gain, voltage gain in decibels, in decibels, okay. So in this way, you can see there will be a graph like this. It will remain constant, and then comes things. Here it will remain constant, okay. So a graph like this, which will be a RC coupled amplifier graph. This is 0.0, okay. So this type of graph will be the relationship between voltage gain and the function of frequency, which is called as frequency response of RC coupled amplifier. Now, what does exactly it indicate? We will see. So if you see a graph like this, your y-axis is voltage gain in decibels. So here you can see voltage gain in decibels, and x-axis is frequency in hertz. Okay, and you can see that this is a graph drawn. So here you are having less gain, voltage gain. Here the gain is constant throughout the mid frequency, it is constant, and here again you are decreasing with the gain, okay. So in mid frequency the gain is constant, so from higher voltage gain, if you come down to 70.7% of the maximum gain, then you will get the frequencies here. This will be called as F1 and this will be called as F2, which are also the half power points. This will be called as F2, and this will actually be your bandwidth. So this will actually be your bandwidth here. Okay, it is a useful range in which you can work with this amplifier. So if you see the bandwidth is, that means the voltage gain is constant, okay, in the range from 50 hertz to 20 kilohertz, that is around 20 hertz to 20 kilohertz, that is the audio frequency range. So this amplifier finds application, it works faithfully, it gives faithful amplification in the audio frequency range, that is from 20 hertz to 20 kilohertz, okay. Now why does the gain comes down at low frequency, why does the gain comes down at very high frequency, and why does the gain remain constant at the middle frequency? That we will see with respect to circuit. Now example, if the frequency is low, if the frequency is low, then what will happen here is the capacitance which is there, the reactance of this capacitance is equal to 1 upon 2 pi fc. So if frequency is low, then xc will become high. Xc will become high, okay. When frequency is low, Xc will become high. That means this impedance, this reactance, this will be more here, this will be more here, okay. So whenever you give an input voltage here, there will be large voltage developed here across the capacitor, because its reactance will be more, okay, because f is less, frequency is less, okay. So that voltage drop will not allow the complete V in to reach the input over here. Okay. Similarly, at the output also, this capacitor will also have Xc reactance as high because that also depends on the frequency. So Xc is equal to 1 by 2 pi Fc. So if F is less, Xc will be high. And because of that, there will be a voltage drop across this also, which will reduce the output voltage. So output voltage will be less when the input frequency is low. That is, you are showing this part over here. So this is the part where the input frequency is low, the voltage gain is low, okay. Similarly, if the frequencies increase little, you get a constant voltage gain, okay. So here, if the frequency is increased, if f is increased, then here in c in for c in, The reactance Xc. So Xc, if you take it again as 1 by 2 pi Fc, and if F has increased, so C will become less. C will become less. So Xc will become less, sorry. Reactance will become less. So if reactance is less, then this C in is acting as a short. This is acting as a short, and C out is also acting as a short circuit. So whatever input you apply here, the same output in amplified version without any loss you will get here. So the voltage gain will be more and will remain more or remain constant for the complete audio frequency range. Okay, for the complete audio frequency range. Similarly, if you come to the high frequency, here high frequency, you can see again the voltage is decreasing. Why? Because when it is again very high frequency, then what happens here? You will get something called as inter-electrode capacitance. Inter-electrode capacitance, which will come into picture only when the frequency is very high. Okay, so this is a capacitance between base and collector. This is the capacitance between base and emitter, and this is the capacitance between collector and emitter. Okay. Now this capacitance, if you see, this will come into picture only in the input frequency is very high. So this capacitance is acting as a feedback from output. This is output and this is input. So output to input, you are giving a feedback. Okay. So the current which was generated at the output in a larger magnitude is again going back to the input. And this is how your output voltage gain will be reduced. Output voltage developed will be reduced because of this inter-electrode capacitance. And even at higher frequencies, the wiring will develop their own capacitance by taking air as a dielectric constant, and this capacitance also see that the AC reaches to the ground and there is a less output voltage. Okay, so that is why at the higher frequency here the voltage gain is very less. Okay, so here it is very less. So here it is roll off, and even at low frequency it is going to roll off. So here also you can see roll off, and but in between for audio frequency range the voltage gain is constant. So this is your useful range of frequency where you can use the amplifier, RC coupled amplifier. Okay. Then we'll go to see the advantages of RC coupled amplifier. The following are the advantages of RC coupled amplifier. Number one, the frequency response of RC coupled amplifier provides constant gain over a wide frequency range, hence most suitable for audio applications. Audio applications, because we have seen that the graph is giving you constant gain for the audio frequency range. And what is the audio frequency range? Audio frequency range is roughly from 20 hertz to 20 kilohertz. So in the graph we see from 50 hertz to 20 kilohertz, the gain is remaining constant, and that is the useful range in which you can use the RC coupled amplifier. So it is used for audio frequency applications. The circuit is simple and has lower cost because it uses resistors and capacitors which are very cheap. Third one, it becomes more compact with the upgrading technology. Okay, so these are the advantages of RC coupled amplifier. Similarly, we'll go to see the disadvantages of RC coupled amplifier. The following are the disadvantages of RC coupled amplifier. Number one, the voltage and power gain are low because of the effective load resistance. Number two, they become noisy with age. And number three, due to poor impedance, matching power transfer will be low. Okay, so these are the disadvantages of RC coupled amplifier. Then we'll go to see the applications of RC coupled amplifier. It is used in RF communications, that is radio frequency communications. It is used in optical fiber or communications. It is used for public address system as preamplifiers. It is used in various controllers. It is used in radio or TV receivers as small signal amplifiers. Okay. So students, this was the explanation of RC coupled amplifier, where we saw definition of small signal amplifier, which is called as voltage amplifier, and in that we saw a common emitter RC coupled amplifier. Okay, then we saw the circuit of it. Then after explaining the circuit and operation of it, we saw the frequency response of RC coupled amplifier, and then we saw advantages, disadvantages, and applications of RC coupled amplifier. Okay, so this was the complete theory on a single stage RC coupled amplifier. Thank you, students, for watching the video.